So this is lecture 1 from University of Vaasa computer vision course. We will use in this lecture slides prepared by Justin Johnson in his course on computer vision in the University of Michigan. So in this first lecture we want to understand what type of problems there are in computer vision. Why do we need to have a separate subject to study computer vision? What are the difficulties? In which tasks is a computer good, better than a human, and what is hard for a computer? So, in one sentence, the idea of computer vision is to provide a computer or maybe a mobile phone the capability to understand things that it sees through the view of the camera. So, for example, if we have a view of a scenery like here, we would like the computer, in some cases, to understand that the view contains a building, also that there is a person walking there, and then there's some grass in the foreground. Then for some applications, we might even want to have some more detailed information about the things that are in the view. So we might want the system to be able to name certain objects or persons to identify individual instances. This, of course, requires that at some point in designing the computer vision system, we have to provide that information to the computer vision system. And especially if we want to make the computer recognize individual people, here we are in an area where we have to consider also data protection laws and so on. So for example, for this view, we would like to make the computer understand that the grass in front of us is flat, and then there is a building which is directly facing us, and above it there is also the sky, which is then infinitely far away. Then if we have a robot or an autonomous device, this knowledge about the 3D structure allows this autonomous vehicle to make intelligent decisions where it can drive and also drive safely, avoiding, for example, humans. In order to find out the 3D structure and also to compare the view that is in the sight of the camera to some examples which the computer vision system has seen before, we have to be able to find matching points between images. So here you have an example where the same building is depicted from two different orientations and also a different time of day. And well-working computer vision algorithms should be tolerant to these types of viewpoint changes. So it should be able to find out that this lower right corner of the building is the same one that appears here in the purple dot on the right-hand image, and so on. Now, why is all of this so hard? Why do we not want to have a complete course or even two courses about this? The thing is that we people, of course, we have trained to do recognition like this since we were born, and for us the brain that we have at use is really super good to find out, for example, matching parts in images and so on. But for a computer, all of this, or at least a part of these problems, are extremely hard. So to make it a bit more concrete why this is difficult, we can imagine that the computer approximately sees something like this through the camera. So these are the pixels how we would visualize an image. But then, if we effectively go to the level of how computer vision algorithms regard the images that can be acquired from the camera, the computer only sees a matrix of numbers, because the computer as such, of course, cannot recognize any objects or know even where an object starts and where another object ends, and so on. All of this, even from the simplest concepts, has to be defined in the algorithms, and in the case of deep learning or artificial intelligence, has to be taught to the computer. So for a computer it doesn't make a difference really if there is a building or a cat in the image. Both of these are just matrices of numbers. And then if there are seemingly really small changes in the camera view, like we move the camera just one tiny bit, the amount of one single pixel, it means that all the pixel values in this image matrix change. And it's even recognizing such a small change that the camera has moved very little requires an algorithm of its own in computer vision. Then if we go to problems related to actual image recognition and recognition of object types, for us, since we have been trained for a long time to recognize various types of cars, various types of animals and so on, we can tell if two different instances of the same animal species or two different, let's say, models of a car belong to the same brand. But for a computer it requires thousands of training examples to make the computer understand that what it sees in the picture, two different examples of the same species, that they exactly represent the same type of animal or so on. However, as a good message, we can also say that in some types of these recognition problems, if we train the computer vision system properly, it can nowadays perform better than a human. And that's of course a big advantage when we want to automate some class recognition, for example. Then for recognition problems, it's also really challenging for a computer to know where in the image objects are. And in some cases, it's really difficult to distinguish the borders of the object of interest. Like here you can see on the right hand side an image of a cat which is in surroundings which have similar colors than the cat itself. Even for us humans, it would be hard, or it would require some concentration to take a pen and draw the exact borderline of the cat in that image. But for a computer it's even harder. Another source of major problems for computer vision systems are illumination changes. So if we are indoors, objects look really different depending on the fact whether we have turned the lights on or if they are off, if there is direct sunlight coming in or not. And then, of course, outdoors we have day and night. In Finland we also have snow conditions and so on. And these illumination changes make the same object appear extremely different in different circumstances. Deformation is also a major problem. So especially living animals, for example, and of course also some non-living objects can be bent and viewed from really different perspectives. And still a computer vision system, so that it could be said that it's robust and it can, for example, detect a cat in any possible position, we have to train the computer vision also to recognize cats in cars or whatever, independent from the direction from which they are photographed. And then for soft objects like animals, which can really bend and get different shapes, we also have to train the computer vision system to be tolerant to such changes. Finally, there is also occlusion, which means that we only see a part of the object of interest. So here on the right hand side there is a case where for us humans, which have a super brain, we of course can identify that there is an animal, probably a cat, maybe a raccoon, hidden under the pillow of the sofa. But for a computer it would be an extremely tough case to recognize that there is a cat in the right-hand view photo. Now, if all of this, and since all of this is so hard, it's also fair to ask, why do we want to go through all this trouble to make computer capable of mastering all of these types of image recognition problems? Well, one good example why we want to do this is the efficiency of a computer. So we are accustomed to the fact that we can go and quickly Google something and maybe find an example image of a certain type of object. So for example, when Justin Johnson made these excellent lecture slides, he probably went to Google and typed their cat, and he found all these nice examples of cats from different angles and different illumination and so on. And if we wouldn't have such recognition systems, also automatic search engines that look through video data and image data would not exist. And going to numbers, for instance, in Instagram, every day 100 million photos and videos are uploaded. And for a human, looking at all this content that is there, introduced in just one single day, would take more than 50 years. So this is something that a human could not even manage, but for a computer, when properly trained, it's possible. Autonomous vehicles were already mentioned before. We still have to wait a few years to see these on our streets, but we can easily imagine that having these in use will be a tremendous benefit for all of us. And in computer vision, or for autonomous vehicles, computer vision is really a top priority. So detecting other vehicles and humans, recognizing the street signs, recognizing the place of the road, must be done super robustly. Then of course we have our local circumstances here with the winter. So deploying autonomous vehicles here in the north, where it's sometimes, even for a human driver, hard to recognize the white road from the white roadside. It's even harder for a computer. So lots of work still needs to be done in computer vision to enable autonomous vehicles in the near future. Augmented reality and virtual reality are also technologies which are coming in the next few years and which will have a big impact to our everyday life. At the moment we can go, for example, and download the Google Animals application, which allows us to project real-sized animals to, for example, our living room. This is kind of a simple but still impressive demo about augmented reality. And example cases like this will come more and more also for serious applications. And also in augmented and virtual reality, computer vision is super important for the reason that computer vision is responsible for locating the position of the viewing device that we have, whether it's a mobile phone, a tablet, or then a headset, in relation to the real world. And it has to be keeping track of the motion of the camera constantly. Otherwise, the augmented reality objects will start hopping in the image and the view is not pleasant to watch anymore. Robotics is a bit related to autonomous vehicles. Challenges are of course a bit different. So in robotics there's also precise manipulation of objects and other tasks which are not so relevant for autonomous vehicles. Then in science and medicine there are also plenty of future application areas. Medical imaging is maybe one of the most important ones. So computer vision is also used for detecting, for example, various types of cancer from X-ray images. And then there are some, let's say, more natural sciences oriented applications like galaxy classification and whale recognition and so on. Mobile phones were mentioned a few times before, but it's still worthwhile to say that the mobile phones that we currently carry around contain a huge amount of computer vision technology, and it's so integrated to the whole system that we don't necessarily even notice its presence. So face recognition was one of the first really successful computer vision applications, and nowadays when you take a photo, your mobile phone automatically from the photo recognizes faces and can also find the similar faces among different images. Then we have, if we look at the slide, the top right image there, where a photo has been taken from a sunset. This is a really difficult scenario for cameras because at the same time in parts of the image there is the bright sunlight, and then if we move our gaze a bit below we have a dark scenery. And this is something that is really on the edge of the capabilities of current cameras, and actually computer vision has to step in here and perform combination of the bright areas and the dark areas and fuse together two photos to make one photo where both the dark areas and the bright areas are nicely visible for us. So computer vision can also be used to extend the capabilities of camera technology. And finally, here in the bottom right edge of the slide, you can see an example of panoramic imaging, which also essentially is a computer vision algorithm, and we will also review it quite in detail in this lecture. So the field of view of normal camera lenses is pretty restricted, and what panoramic imaging does is that you rotate the camera at the time when you are photographing the scenery, and then the camera takes a series of shots and then algorithmically combines those into one single photo. Then one example which isn't depicted here, but then which is becoming more and more mainstream, is also 3D face recognition. So if you have, for example, one of the latest iPhones, they also have this depth camera in the smaller camera, which is facing the phone user, and using that depth camera allows the phone to make a 3D photo of your face and do face recognition, which is so robust that it can also be used as a safety feature of the phone. Then in the last parts of the lecture, where we talk about 3D computer vision, we also look at 3D reconstruction, which is important, for example, for remote sensing, which means that let's say a drone is flying above the city or above the forest, and it wants to make a 3D map of the city or the forest below it. And so 3D reconstruction allows, for example, a drone equipped with a basic camera to fly around a certain area of interest and take a video capture of that area. And then by using 3D computer vision, it's possible to make an accurate 3D reconstruction of the area which was seen by the camera of the drone. And finally we can get the 3D model and use it for other purposes. Recently then, some novel application areas have emerged, especially in deep learning for computer vision. I quickly show here a few examples. So one thing made possible by deep learning is, for example, super resolution. So if we have a low resolution input image, we have a tiny picture of something, and we would increase the precision of the image and still make it look natural. We can use some deep learning algorithms for that. So here on the right hand side, you see how the image in reality looks like at higher resolution, and then here in the middle you can see a version of the image which has been generated by computer vision only from this low resolution input image from the left. So you can see that the algorithm has successfully increased the amount of detail here, but since the input here on the left hand side really is missing a lot of information, you can see that the algorithm has introduced some details which in reality are not there, but still which could be there. So the computer has kind of hallucinated some more details to the photo. Then it's also possible to do something called style transfer, which means that a natural photo is taken and then the user picks, for example, the style by his favorite painter, and then the computer vision algorithm transforms the natural photo as if it would have been painted by a certain artist. And then there are other a bit more fun applications, like you can draw something and then the computer hallucinates some additional texture or detail to the image. Then in terms of image generation, one particular application which also maybe has serious consequences to well, maybe not everyday life, but to some security cases. It's possible nowadays by terms of computer vision to generate images of people that do not exist. So the algorithms nowadays are so good in generating really detailed images that it's possible to create thousands or, well, any number of persons that do not exist, but the photo is so detailed that not even an expert can tell whether this is a real person or one generated by the computer. This is of course nice for maybe shooting a film or so, but then if we go, for example, to politics, maybe Facebook or the like, where fake profiles are nowadays quite common, this of course also gives some means to adversarial persons to like post opinions from some people that do not exist, and also create realistic photos of them in various circumstances. So all of these examples that I showed in the end are only possible because machine learning has had so big advances in the last 10 years. And the majority of our course also concerns these machine learning algorithms, and to this extent we will also quickly take a look how machine learning has developed in the last 10 years and which advances have made machine learning as good performing as it is nowadays. So first I want to clarify a bit about these concepts of artificial intelligence, machine learning, and so on. So artificial intelligence usually is the overarching concept that includes all kind of decision making that a computer has been trained to do. And then machine learning and computer vision are often considered as subfields of artificial intelligence. So machine learning includes all kinds of techniques where the computer is provided with example data, possibly labeled by humans, and then the computer itself trains itself to do, for example, recognition based on the examples. Computer vision has a lot of overlap with machine learning in the sense that computer vision on one hand gives machine learning the tools how to work with images, but also the other way around, so that machine learning provides the necessary techniques to make computer vision algorithms learn from examples. And then deep learning, which is the buzzword nowadays, is a subfield of machine learning. Shortly stated, deep learning is an area where the complexity of the learning algorithm starts to be so high that it's not anymore easily tangible for a human. So deep learning algorithms concern algorithms which have thousands or millions of parameters that the algorithm is learning from data, and also complex interconnections between the learned data, so that it starts to be really hard for human to understand how a deep learning algorithm works. But going to the history of computer vision and also a bit machine learning, if we start from the 1980s, computer vision at that stage was approximately at this level. So if we have a clear input image with some specific objects, in the 80s approaches like edge detection were developed, which allowed them to extract the boundaries of certain objects. This appears to be really simple, but it still has consequences nowadays. So also companies that we have here close to Vaasa, which are in the manufacturing domain, where there are production lines automated by computer vision, these simple algorithms like edge detection and so, which can be done super fast and super robustly by a computer, can really make the production line more efficient compared to the alternative that the human would be there doing the similar task. In the 90s then, computer vision evolved in one sense, so that from detecting boundaries, then also certain regions of images could be combined, so that it was possible to say which regions of the image belong together, and through that recognize individual objects. At the same time, also between the 1980s and 1990s, there was a period called the AI winter, which was a period of time where the development of artificial intelligence almost stopped. The reason for that was that in the 70s and in the 80s, when there was a boom in artificial intelligence, really big expectations were put to artificial intelligence, but since the development in AI wasn't as big as the expectations, the institutions that funded research of AI became kind of disappointed and stopped funding AI research, and as a consequence there was a period when nothing new happened there. But computer vision at the same time still had some advances. Then going a bit further to the early years of this millennium, recognition with matching common points of interest between images was to a large extent developed in these years, and this is really super important still nowadays, especially for 3D computer vision. One of the most important works from these years is the feature descriptor called SIFT, which was introduced in 1999, and we will also talk about it in this course. Then a bit later, the first commercially successful application of face detection also emerged, and soon after that data sets were released for visual object recognition. And the role of these various data sets was really important for the computer vision, because they were related to competitions where research teams and companies around the world could participate in this competition with clearly set rules and try to develop algorithms for certain challenges like object detection. And then of course all the publicity that would come through winning these challenges made the computer vision really advance through these data sets and challenges. One of these first data sets, like this Pascal data set, quickly proved to be too simple for computer vision algorithms, and soon after that, in 2009, this famous data set called ImageNet, and also the challenge related to it, was released. This challenge consisted of more than 1 million images, which were labeled into 1,000 different object classes, and then the challenge was to recognize as successfully as possible the different object classes in these images. And this ImageNet challenge was also one of the major drivers of the breakthrough in deep learning. So in the early years, when deep learning was not yet every day in machine learning, so in 2010 and 2011, the success in this ImageNet challenge was rather average. But then in 2012, when Alex Krichevsky and his colleagues introduced a deep learning algorithm which was very successful in this ImageNet challenge, that really started the big boom in deep learning. And you can see that in this bar chart here, where a lower number is better, we can see that starting from 2012, the results in this ImageNet challenge have become better and better every year. And approximately in 2014, the performance of deep learning algorithms was already better than human capabilities in image recognition. The type of algorithm that Alex Krichevsky and his colleagues used for the good success in ImageNet was a convolutional deep neural network. Deep neural networks are trained by backpropagation, which originally was introduced in 1986, but then only in the later years the concept of backpropagation was then properly applied to deeper networks and convolutional neural networks. And then from 2012, when Alex Krichevsky and others introduced the AlexNet, and it was so successful in ImageNet, this deep learning explosion came and really made deep learning mainstream. So nowadays these convolutional neural networks are everywhere. They dominate in image classification, image retrieval, which means that we give an example of an image and then the computer looks for similar images, or we type a word and then the computer looks for images that describe that word. Object detection also, all done by convolutional neural networks, image segmentation, image captioning, so the computer generates a descriptive text from the view that is seen in the image. And what made deep learning successful in the early 2010s essentially consisted of three components. So first of all, the algorithms, convolutional neural networks, and also back propagation. And then a second component, which maybe is not so recognized so often, is the availability of data. So in the early 2010s, people started uploading millions and billions of photos, for example, to the internet, and all this image data, often accompanied with some text description, it served as excellent training material for deep learning, because you might know that the deep learning algorithm needs to have thousands or millions of examples to train robustly. And without having all that data, it's not possible to create a deep learning system. And then the final component was the sufficient maturity of computing hardware, especially graphics processing units, which initially were designed for gaming purposes. But then around 2010 or a bit before, researchers noticed that these devices developed for gaming were actually really good for training machine learning. Since then, the development of graphics processing units has also rocketed quite a lot. So if we compare the present status, how many gigaflops of performance we get for the same amount of money compared to maybe 2010, the difference is quite big. So in 2010 approximately, it was possible to get some 3 gigaflops of compute performance with $1, and nowadays you can easily get 12 gigaflops of performance. And very recently, GPUs have also been heavily tailored for machine learning in the sense that they have some special hardware just for purposes of machine learning.